This is a continuation of Test 3 review questions, and I realize there's a lot of videos here, but they've jam-packed lessons 10, 11, and 12 with a lot of information, so I'm trying to make sure I hit all of the high points that are listed on the review. And in the next section, with questions 21 through about 24, they're focusing on polynomial functions, but they don't really define for you, at least on the review, what a polynomial function is. So I want to begin with that statement that polynomial functions of x are functions, so they're going to be made up of variables and letters with exponents, but the key thing is that all of the exponents on the x are whole numbers. And I've given you a variety of examples. In these particular problems, you can have exponents like x to the third or x to the fifth, x to the 10th. You can have any. And the higher the exponent, the more complicated, if you will, the graph of that particular polynomial function is. And yes, we can plug the polynomial function into our graphing calculator, but if we know some things about it ahead of time, that becomes helpful. And so one of the things that they focus on is looking at the end behavior of the particular polynomial function. It's also referred to as the leading coefficient test. We can look at the leading coefficient and identify and get an idea of what should be happening on the ends of the graph as you go further and further away from zero towards negative infinity, or as you go further and further away from zero towards positive infinity. What should the graph look like? And there are really 4 different scenarios, and I want to kind of walk through those using a couple of PowerPoint slides here. So I'm going to back up to this PowerPoint slide. And basically, the leading coefficient test, or to determine the end behavior, you want to look at 2 things. First off, you want to look at the degree, which is the highest exponent. Okay, so the degree of the polynomial is the highest exponent. We usually use the lowercase n to represent that symbol. And we want to focus on whether that highest exponent is either even or odd, because that's going to help us determine what should happen to the ends of our graph. Second thing you want to focus on is the leading coefficient. The leading coefficient is the number in front of x with the highest exponent. Okay, so the leading coefficient is the number in front of x with the highest exponent. And we want to focus on whether that leading coefficient is simply positive or negative. I don't really care what number it is at this point. I just want to know, is it positive or negative? And I've tried to describe what's going to happen both in words and in symbols. And the symbols look very daunting, but I know that's what they use in lesson 11, as well as on the test. So you need to be familiar with that. So basically, what happens if you have an even degree and you have a leading coefficient that is positive, then basically what happens is you go further and further out towards negative infinity, the graph continues to go up towards positive infinity. The same thing happens as you go further and further out on the x to positive infinity, the y value continues to go up towards positive infinity as well. Verbally, we say it rises to the left and right. In symbols, we say as x goes to negative infinity, f of x or y goes to positive infinity. Or as x goes to positive infinity, f of x goes to positive infinity. So if you have a leading coefficient that's positive and an even degree, both ends are going to go up. Now this test doesn't really tell us what's happening in between those 2 endpoints, but we at least get a sense of what's happening on the ends. If you have a degree that is even and the leading coefficient is negative, then basically we say that it falls on the left and it falls on the right. As x goes to negative infinity, f of x goes to negative infinity. As x goes to positive infinity, the f of x goes to negative infinity. Notice when you have an even degree, both ends do the same thing. They either both go up towards positive infinity or they both go down towards negative infinity. Next, you think about if the degree is odd. Again, the degree is that highest exponent. Is it odd? Odd would be values like 3, 5, 7, 9, and so forth. And again, you have to think about that leading coefficient and whether it is positive or negative. And one thing you're going to notice about this is if the degree is odd, your ends do opposite things, meaning one's going to go up and one's going to go down. It's just a matter of which one does which. For a degree that is odd and the leading coefficient is positive, the graph, as it gets further and further away from 0 towards negative infinity, it falls or goes down to negative infinity. As it goes out to positive infinity, it goes up or rises on the right. We say it falls on the left, rises on the right. As it goes to negative, it goes down. As it goes to positive, it goes up. If it's odd and the leading coefficient is negative, then it actually will rise as you go to negative infinity. F of x goes to positive infinity, and it falls on the right so that as you go to positive infinity, f of x goes to negative infinity. And again, notice how each end does opposite things. So let's take a look at a couple of examples on our review sheet here. Question 21, it says determine the end behavior, and it gives you the polynomial. Now, typically polynomials are set up so that the highest degree is first, and then it goes down in descending order of exponents. So this goes 4, 3, 2, 1, and then none. Remember, we're looking for that highest degree, which represents our exponent, or is our highest exponent. In this case, our degree is 4, and 4 is even, and my leading coefficient, which we denote by a sub n, the number in front of that x to the fourth is a negative 5, which is negative. So I have an even degree. My leading coefficient is negative. So verbally, I know that my graph is going to fall left and right. If we write it in the math lingo, we would say as x goes to negative infinity, f of x goes to negative infinity. And as x goes to positive infinity, f of x goes to negative infinity. Again, both ends do the same thing. If you look at the next example, we have a high exponent. Our degree is 5, which is odd. Our leading coefficient is negative 3, the number in front of the x with the highest exponent. It is also negative. If it's odd, we know that the ends do opposite things. Verbally, we would say here that it rises left and falls right. In the symbols, we would have x goes to negative infinity as f of x goes to positive infinity, and as x goes to positive infinity, f of x goes to negative infinity. And it may help you to kind of be familiar with the verbiage, with the words, and then be able to translate the words to the symbols. The second thing they mention here is just a simpler way to solve the problem. Instead of having to plug and chug into that big, long polynomial function to find the value, we have a shortcut that's called the factor theorem or the remainder theorem. And basically I can use synthetic division to help me figure out the value of a particular x. By doing the synthetic division, the remainder is what tells me that its value at that particular point. They don't give you any problems related to this. There are none on the test related to that, but they do mention it. So obviously it's something they want you to know at some point down the road. The third thing that they list here is the idea of listing the possible rational zeros. Technically, with a polynomial function, really any value that you can possibly think of in our number system is a possible solution or a possible value that fits or works within that polynomial function. Well, gosh, that's a lot of values to think about. So if I'm just asked to find the zeros or find the x-intercepts of a polynomial function, I could be sitting here all day long because I'm just randomly guessing. And so there's a theorem. It's called the rational root test or the rational root theorem, sometimes called the rational zero theorem, that helps to narrow that list. And in that rational root test, we look at the relationship of the factors of the constant, which is basically just the number at the end of the polynomial, in relationship to the factors of that leading coefficient that we were using just a few minutes ago on the leading coefficient test. That's the number in front of the x with the highest exponent. And so it helps us to narrow that list. So in this polynomial that we have here, and they don't even give us the full polynomial. They give us the first term, 3x to the fifth, and the last term, which is 12. They don't give us all the in-between. We really only need those two numbers. The constant here is the 12, and the leading coefficient is 3. So if I think about the numbers that I can multiply together and get 12, I could do 1 times 12, 2 times 6, 3 times 4. And I do have to allow for the possibility that they are positive or negative because I don't know what they are. And then to think about the factors of the leading coefficient, I can multiply together 1 and 3 to get 3. And then I want to look at the ratio or the comparison of each of those numbers. So I would have plus or minus 1 over 1, plus or minus 2 over 1, plus or minus 3 over 1, plus or minus 4 over 1, plus or minus 6 over 1, plus or minus 12 over 1. I'd have plus or minus 1 over 3, plus or minus 2 over 3. 3 over 3 would be 1. I've already got that in the list. Plus or minus 4 over 3. 6 over 3 would be 2. I've already got that in the list. 12 over 3 would be 4, and it's already in the list. So ultimately, I've narrowed it down from a bazillion, jillion possibilities to these 18 possibilities, because you have 9 options and you have to consider both the positive and the negative. So we have plus or minus 1, plus or minus 2, plus or minus 3, plus or minus 4, plus or minus 6, plus or minus 12, plus or minus 1/3, plus or minus 2/3, and plus or minus 4/3. That's our list. So we've gone from having a bazillion jillion options to 18 options. Now in the next video, we're going to talk about Descartes' rule of signs. And Descartes' rule of signs helps us to even narrow this list further.